So this is Chrome multi-process architecture, seat of the pants edition, I just want to take some time and give everybody sort of lay of the land. Try to explain, paint the broad picture of how everything works, and talk about some of the things that we had to do in order to make it all work well. And then I want to try to leave enough time for people to ask questions, because hopefully there'll be some interesting questions so we can dive into some interesting things. So some of this will be review if you read some of the design docs, but I'll just get right into it. So first of all, what are some of the goals of the multi-process architecture? Well, we wanted to make sure that what we were basically going after is we really wanted to make a very stable browser, fast, and secure. And we recognized that one really great way to improve on all these fronts was to divide up the browser into multiple processes. So when I talk about stability, though, there's more than just dividing the process up into multiple processes in case the renderer crashes. We also want to make sure that the renderer can't do anything to make your browser hang or lock up in interesting ways. And we also want to make sure that essentially the main process that was actually driving the whole user interface would always be able to show some recent representation of the web page, such that even if the renderer was out to lunch or running garbage collection or doing some crazy thing, we'd be able to show something meaningful to users. And this is sort of a guiding principle for a lot of things, which I'll get into later. We want to make sure that related to this, we want to make sure all the communication was very asynchronous and not blocking in weird ways that would cause the user interface to be janky. So that's stable and fast. Well, we recognized that by dividing the browser up into multiple processes, we could see benefits on multi-core systems. That's one thing. We saw that if you have many different applications going, well, they can all be running independently. Great. But what I want to talk about here also is that we found that even in the case of rendering a single web page, we could derive some benefits from multi-core. So I'll talk about that in a bit. Secure. Well, at the very beginning, we thought, we had no idea we'd be so lucky as to hire a team of sandboxing experts. But it seemed reasonable that if you had a separate process for your rendering engine, that you could probably do something to limit the harm if it were ever corrupted. Turns out that we were able to bring on a team of experts in this area, and that led to us pushing really hard to separate the renderer as much as possible from the operating system so that it was easy to sandbox it. So I'll talk about some of that. So here's some of the goals. First of all, though, I want to draw another picture just to give you a diagram of sort of some of the terms. So what we're trying to do here really is bring WebKit into the browser in this multi-process way. And so WebKit represents a rendering area using something called a web view. And so we basically have this thing that renders a web page that we needed to have running in the sub-process and then get its pixels and put it on the screen in the main process. So we wrap the web view with something called a render view. And then this guy talks, as I'll talk later over IPC, to something called a render view host. So this is in the browser. And then here's in the renderer process. A renderer. And view here has no relation to views. Okay, yes. Peter made the comment that when we say view here, we're not actually talking at all about Chrome views, which was actually developed much later. And to add confusion, there's actually a class in WebKit called Renderview. But we don't mean that. We mean the class in Chrome called Renderview. So this is the WebKit side. Over here. And essentially what you'll see in the code is that there's a web view contained by Renderview, which then does IPC plumbing to something in the browser called a Renderview host. So another picture real quick. Stitching it all together. If you actually get down and look at the code, what we have in the browser, as I mentioned here, we have these things called Renderview Host, which is actually corresponds to a native widget, like an Hwind in Windows. And we can have multiple of these, one for every tab. Okay, and then on the other renderer side, we have a corresponding render view. Again, one for each tab. And these guys, if they're all, of course, as I've drawn it here, these are all in one render process. So these are the corresponding objects in the browser for those guys. And they talk to something called a render process host, who then over IPC is communicating to a corresponding render process. So this is actually, this diagram shows the Ipc flow. If a Renderview host wants to talk to his peer, he has to send a message through his render process host over an Ipc channel to that guy. And so messages between Renderview host and Renderview, we call them routed messages. Just want to get all the terminology down. Routed messages. And then messages that just terminate at the process level, at the render process host or at the render process, we call those control messages. Okay, so as I talk about some of the other stuff, this hopefully will help. One more thing you'll see if you're in the code actually is that Renderview and Renderview host, they have a base class called RenderWidget and RenderWidget host. I bring that up because there's also over here something called a web widget. And conceptually, this divide is simply between things that are purely just graphics related and things that are add to that web page related stuff. So the concept of loading URLs is at the render view level, web view level. The concept of just displaying pixels and dealing with input and scrolling and cursors and so on is at the widget level. And we also reuse render widget, web widget, and so on for other types of UI elements that are driven by WebKit but actually don't have anything to do with loading pages, which are things like drop-down selects. So if you have a select menu in the web page and you click on it, it brings down a little pop-up window. That pop-up window's contents are rendered by WebKit, but it's important to note that that pop-up content area isn't contained by the owning render view. It can actually extend beyond the bounds of the frame, so it really needs to be its own top-level HWind. So we reuse the render widget for that kind of stuff. Okay. So now a little bit about IPC. When we first started this project, a lot of people were like, well, just use COM. That'll solve all your IPC problems, and it kind of gets you everything for free. WebKit already at that time had a COM interface on Windows, so we tried that a little bit. COM had this sort of fundamental limitation, though, that the IPC was synchronous, or if you try to do it asynchronous, it's not fully asynchronous. And so the performance wasn't there. The kinds of stability properties we were looking for weren't there that I talked about earlier. Essentially, if we were blocked on a renderer from the browser side, if we were blocked on the renderer, we were hanging the browser and then we were having bad UI. So we really wanted to make sure we had a very asynchronous model for IPC. So then we went and just said, well, let's just use a pipe. And we ended up using a named pipe. And we use asynchronous I/O over a named pipe. That's great. Now we can send asynchronous messages. What we ended up doing, though, we ended up needing, in some cases, synchronous messages. And so we, for example, we found that there are plenty of times when WebKit needs some information, and we need it now. And so that's a synchronous IPC where he blocks until he gets a result. But we decided that we will never do blocking IPCs from the browser side because this whole problem of maybe the renderer won't respond, and we want to make sure the browser is always responsive. Okay, so this sort of segues to talking about threads a little bit. So I thought as part of this talk I should give a little bit of description of the threads in Chrome, because it's not always obvious. You hear people talk about the IO thread, the DB thread, the file thread, what the F thread, and maybe it will help to know why we have the threads we have. So in the browser side over here, we have something called a UI thread, which is where almost all the native widgetry runs. Okay, and we have an IO thread, which is where we handle the IPC traffic, network loading, and various other kinds of what I'll call routing type events. So this thread tries really hard to never be stopped on anything, and it tries to be purely asynchronous. So then we necessarily need a different thread for cases when we need blocking I/O, and that ended up just as the evolution of things being called the file thread. And this is where we do blocking I/O, as well as use COM when we need to talk to the OS, or shell 32 calls, because all these things just are really awful. They can hang your browser for a long time. So we don't want to use them on the UI thread if we can help it. There's some small exceptions because we use a C-rich edit control here, which turns out to use COM under the hood. It's actually a huge contributor to why Chrome might not be as fast as it could be to start up. Ask Peter about that one. Then there's the DB thread, where we use SQLite. And there's a few other random threads, but these are the main ones you'll hear people talk about. Now on this side, in the renderer side, we also have an I/O thread as well, which again used to receive IPCs, process IPCs, and then we have something called the render thread. And this turns out to be the WebKit main thread. So WebKit is a single-threaded, except for more recently where it handles worker threads, but traditionally or historically it's always been a single-threaded kind of library, and this is the main thread where all the WebKit action happens. And so to implement things like synchronous IPCs, the render thread gets blocked on a mutex, but the I/O thread here services the IPC to this thread here, where then some answer is provided and back to this guy. There's one thing that I just really want to bring up while we're talking about threads, because I think it's something that is really easy to get bitten by, which is that when dealing with synchronous IPCs, like say you were implementing some new web API where you, like local storage or session storage or things of this nature where you need the data now, because the JavaScript application wants a result. It's tempting to, you start out with a synchronous IPC, and the traditional way that one might handle an IPC coming from a render view is to handle it in the Renderview host. But the Renderview host is an H-wind, has an H-wind. It's actually living on the UI thread. And so if a synchronous IPC comes from here all the way to the UI thread, this actually turns out to be a huge problem for us. And it's not obvious from what I've written up here why, but plugins tend to be are the source of this problem. And you can end up with deadlocks. And I'll spend a little bit of time explaining this because I think it's really helpful for people to know. So in Windows, when you have H-wind, I'm going to draw pictures of H-winds here, where the green one is a plugin, like Flash. Okay. Flash allocates its own H-wind, and Chrome has its outer H-wind. Well, when you do this kind of thing, because we're running plugins out of process, there's actual synchronous communication that Windows does between parent and child H-winds. So it's possible for our browser UI thread, thanks to Windows, to be blocked waiting for Flash to do something, like paint itself or service an input event. And it turns out that Flash itself can also do things like script the page. He can execute script in the outer page. When he executes script in the outer page, because we're running Flash out of process, what he's really doing is sending a synchronous IPC to the renderer, to the render thread, saying, please execute the script for me. Well, while that's happening, he's not going to be responsive to these incoming Windows events. And so if the render thread were actually, at that time, trying to communicate over to the browser UI thread, we could deadlock, because the browser UI thread might be blocked on the plugins. You get these nasty deadlocks. So we just have this very simple rule in Chrome. Any synchronous IPC coming from the renderer should terminate at the IO thread or one of these other background threads. But it should never terminate here. Never at the UI thread. And then we're safe. We can allow all kinds of crazy synchronous IPCs that are doing weird things, and everything's happy. So then, okay, now I really want to move on to some more interesting things. Painting. Everybody got this? So, painting, scrolling, resizing, restoring tabs. All of these things, what they have in common is, these all have a lot in common, which I'm going to talk about. So, I mentioned very early on, in order to achieve these nice stability properties where it looks like the browser can always be responsive to the user, we're showing a possibly old representation of the pixels for the page. So every Renderview host has a backing store, which is the bitmap of the last rendered version of the page. And the pixels for that come from the render view, which has functions like paint to produce pixels, and WebKit through this area will call back and do things like invalidate, erect. So we will observe, the render view will be observing invalidates from WebKit, and when he wants to, he can ask WebKit to paint and produce pixels. And then what he does is ships those pixels over to the Renderview host, and the Renderview host puts those pixels into his backing store, and now we have a representation stored of the page that we can always put on the screen when he gets a WM paint. This is the Windows message saying, hey, look, you got to put something on the screen because I don't have anything. And so what we'll do then is just from the backing store put it on the screen. So painting in the browser now doesn't involve the render at all. We can always just paint from the backing store, and things are fast. Splitting from the backing store is fast. Asynchronous to that, the renderer can update it. Early on, we built this system and it was working, but I noticed some funny things. Like if you take Google Maps and you grab the Google Map and you actually try to move it, sometimes it would never see the pixels on the screen changing, but the CPU usage would spike way up, and you're wondering what's going on. Turns out that over here we were doing fun invalidate paint kinds of operations, getting lots of invalidates, doing lots of painting, shipping bitmaps over. And meanwhile, on the Renderview host side, we were receiving mouse inputs, sending mouse events over. And all this was going on, but we were never getting a WM paint. Turns out that input events on Windows always take precedent over painting. And so that was fun. So we had to then add something to make sure that we never produce a bitmap unless we got it on the screen. So that was some interesting accounting that we just had to do. And then as a result, we don't have this problem. So we built an acknowledgement-based system. So there's an IPC that says, something like, I think it's called paint rect or something, and he carries with it some shared memory bitmap containing the data for the invalid region or the newly updated region, and then he has to send back an acknowledgement. And then based on that, everything kind of works much better. Because of most everybody was on dual core at the time, no one ever saw that problem with Google Maps. It was only when you got on a single core machine. But an acknowledgement-based system works great there. Scrolling is very similar. The thing you want to do with scrolling to get very good performance is you want to basically, suppose you have, these are all the pixels on the screen. What you really want to do is, suppose you're scrolling down, you want to take the region that's still to be on the screen and just shift all those pixels down to here. And then fill the exposed region. So scrolling. Yeah, okay. He worked on the scroll work. He's right. But what's going on here is that an input event makes its way to WebKit. WebKit's like, hey, that hit a scroll bar. Scroll bar did its thing, said move, scroll the page. We get a command here that looks very different than invalidated. It's called something like did scroll rect. He gives us the rect that should be scrolled, and then dx, dy. Then what we do is we set up the same kind of thing. We want to send an IPC that says scroll rect, passing the same parameters. We also call paint in order to generate this region. sending that bitmap along with the dx, dy, and so on. Renderview Host then says, well, I need to perform the same operations on my backing store. He takes his backing store, he shifts the pixels down, fills in the exposed region, and now he can, tell the H-Wind, hey, look, we need to do a scroll operation, and then when that scroll operation happens, he's reading all the pixels out of his backing store again. So they're very decoupled. So the render is decoupled from painting, actually, the screen. But because we were actually getting dx, dy in the bitmap, we can do things like use Windows APIs like scroll DC and scroll window to actually do optimized scrolling on the H-Wind and to give the graphics system knowledge that we just want to do these shift of pixels and backfill, which allows scrolling to be low CPU usage. It turns out that some pages that have like fixed position content defeat optimized scrolling because you always have to, you can't just shift pixels down. You have to re-render stuff because of overlapping things. This is a problem in Gmail, like with the little chat windows that come up. So Gmail scrolling slow because that chat window it's always interfering with the content below it. Anyhow, resizing. Resizing is kind of interesting because what's happening there is, I'll just erase part of this. With resizing, what's happening is that we have the outer window, H-Wind. User grabs the corner. Windows tells us, hey, look, your size changed. And then right after that, he says, now paint. And if this is a case where the backing store is not good enough, our backing store is small, but Windows just, we now need new pixels, so what do? This is where we ended up sending an Ipc down to the renderer to have him produce the new pixels for the whole thing. And then we do wait. Then we wait a little bit. Like, I forget how much, maybe up to 40 milliseconds or something reasonably small. We wait for our I/O thread to receive an Ipc that actually carries with it the shared memory for the new rendering. And so if we get it in that enough time, then what we will actually be able to display is unperceptible to the user. We actually now got the new pixels, and they never see the old representation at the wrong size. However, I'm sure anybody who's used Chrome knows that oftentimes you'll get this little white border here where we didn't have pixels yet, and we're still catching up. And mostly that's limited by how fast WebKit can relay out the whole page as a result of a resize. So Gmail, this will always happen. Google.com would never happen. Anyways, Google.com has a white background. So it turns out that because we're using these backing stores to get good performance in the browser, we're also using a lot of memory. And so if we have a lot of tabs, we'd be using a lot of memory because we have a ton of backing stores, and that's kind of bad. So we need a cache, obviously, have only so many backing stores. So then what about tabs that you haven't been to a while and you go back to them? What are you going to do? Well, it's kind of similar to the resize problem. You don't have a backing store, but you need it now, so we use the same trick. Ask the renderer to produce pixels, wait just a little bit, see if he can produce them in enough time. And if he does, then it's all seamless. And we actually ended up extending this. We said that even foreground tabs, because you could have a lot of windows, even foreground tabs could potentially lose their backing store. And if the user interacts with that page now, we have to go get the backing store, fill it again. And the same trick is used there. It all kind of works. I said I would save time for questions, so I'm going to just end there and ask if people have questions. Is there anything you want me to talk about, or should I go on? 5 minutes. I'll just go on. Okay, sure. So I mentioned a little bit in the beginning about events. Turns out that I don't want to talk about that. I'll talk about sandboxing a little bit more and some of the security stuff. Some of the stuff we did to facilitate security. So as I mentioned with plugins, H-Winds can be multi-process. You can have a different H-Wind for a child process. So why not just use H-Winds for the renderer? Why do all this crazy stuff I just got done describing? Well, turns out that we just lose the ability to sandbox this effectively because there's these connections between child and parent H-Wind. It'd be possible for the renderer, who is a corrupt renderer, to mess with the window hierarchy and thereby screw up the browser in interesting ways. Also, HWinds like this would reveal information about the desktop. And one of the things that the sandbox achieved was literally running the renderer with a different desktop. So it's running on its own virtual desktop. So it's such that if there were ever any kind of hole in the sandbox that allowed people to play with user32 libraries, all they'd be getting is user resources for a different desktop. And so this adds another level of security just to kind of keep user input and other kinds of things away from this renderer as far away as possible. Right. So this really necessitated getting all the Windows isms out of the renderer and moving to this sort of more in-memory kind of approach.
Isn't there one other reason to not use HWinds for renderers, which is to not interlock the message loops and thus possibly hang our browser if the renderer hangs up?
Yes, what Peter said. With all the synchronous IPCs that happen between HWinds and Windows, we have a potential problem that the child window is blocked waiting on its parent for something. And I explained earlier that whenever we have a situation where the render thread is blocked potentially on the UI thread of Chrome, bad things can happen. So this actually, for a number of reasons, turned out to be very necessary to just get the HWinds out of the render process.
Which means we can still lock the browser UI on hung plugins, necessitating the hung plugin detector, right?
Yes. So if anybody's seen that, if you wait long enough after Flash locks up, if you wait 30 seconds, I think, you'll see a little dialog come up offering to kill Flash because we detected that it's not responsive and that it's brought down or wedged the whole widget hierarchy it's associated with. We use the same kind of API that Windows does to figure out that it should put up the little end task dialog or unresponsive treatment in the title bar of your application. Any other questions? Okay, then I'll just throw out one more interesting thing. Turns out because we're multi-process, Ojan reminded me of this. Turns out because we're multi-process, we can do things like potentially just terminate the child process when we close a tab. If the child process has no unload handlers, if the web pages in there have no unload handlers and no on-before unload handlers, then the web page anyways has no idea if it's gone. So we look to see, did the web page have any of those kinds of event handlers? And if it doesn't, then when we want to kill it, we just call terminate process. And it turns out to be really nice because then tabs close quickly. Okay, and